Okay guys, here is the third video, and this one is going to help you with the A assignment for this project. So you may notice the sheet's a little different from where the last video left off, and I just spent a little bit of time cleaning it up when we left, but it still works the way that it did before. We have our time counts up, our altitude is based on our old altitude, B7. Now if I can go in here, it's based on our old altitude plus our old velocity times our time step. Our velocity is equal to our old velocity plus our acceleration times our time step. And then our acceleration formula is equal to big G times mass of the planet divided by R, which was the radius of the planet plus the altitude, the quantity squared. Okay, so we spent a whole bunch of time making this formula work, and unfortunately, it's not correct. So our acceleration for a rocket is not negative 9.81 when it's on the launch pad. If it were, it would start going downward, because there's another assumption we have here that's wrong. Its initial velocity is not 11,200 meters per second. Its initial velocity is 0 meters per second. So if it started out at 0 meters per second and was accelerating downward, it would just dig a hole into the earth. And that's not what rockets do. So let's go over here for a second and draw a little tiny block picture. Let's say this orange block is my rocket. Well, there's two forces acting on it. Fg is pulling it downward. Watch this, we'll be creative with letters, is pulling it down. Meanwhile, Fr, the rocket, is pushing upward. So we have a case where there's two forces, one pulling down and one pulling up, and if the rocket works, Fr is bigger, so the rocket goes up. Now if we add these two together, we get a thing called F net. That's our total force on the object. And our acceleration, A, is equal to F net divided by mass. So really, when we did this formula over here and said our acceleration is equal to G times mass of the planet divided by R, we weren't actually calculating the actual acceleration of the rocket. We were calculating what the rocket would accelerate if only gravity were pulling on it. Since that's no good, let's get rid of this. Now, before you get upset, we can take this formula and keep it if you'd like, but it's probably easier just to do it from scratch again, so I'm going to get rid of it. All right. Now, let's start from scratch. Oh, did I break it? Kind of. What is my actual acceleration? Well, it's pretty simple. And this is actually a good thing. We're getting back to simple stuff. It's equal to F net divided by mass. Well, I have a problem here, though, because I don't have an F net yet, and I don't have a mass anywhere on the screen. So we really need these things in order to be able to keep moving or keep working. So let's get them. Let's make a new column here called F net. And we'll make, we know that F net depends on Fg and Fr, so let's make two more columns, Fg, Fr. And then we also know that we're going to need mass, so let's put another column for mass. So we got all these different columns now. And let's make them stand out a little bit. There we go. I'll make this whole row the same color too. So we now have lots of columns. What does F net equal? Very simple. F net is equal to Fr plus Fg. Again, simple formula. Doesn't really require much work. How about Fg? What's that equal to? Well, we kind of already did this. Fg, the formula, is equals G mass times mass of the planet divided by R squared. So this is kind of like the formula we just had for acceleration. The only thing is mass is still in there. So let's include mass in there. Let's do this again. And we can copy this formula if we really would like. Like I said, we weren't going to get rid of it. So I'm going to copy this formula, and I'm going to put it right here. And let's see what we need to change. G times M. Well, we didn't have M in there, so let's throw it in. Right between these two multiply signs, we're going to say H7. Current mass times mass of the planet, which doesn't change, divided by the radius of the planet plus the altitude. All set. This is exactly the way that we want it now. Now it's given me the value 0 because I have no mass yet. This is a number that you're going to get from me. I think it's on Schoology. And we are going to be using the mass of the Delta IV Heavy rocket. And when the rocket is on the pad, the mass is the empty mass plus the fuel mass. Oh, and it's giving me an error because I put in a formula. Let's put this in quotes. Empty mass plus the fuel mass. Now, that'll come out to be a number, and we'll come back to doing this later. For the time being, just so that this doesn't have error messages all over, I'm going to put a number in, and I believe that the rocket's mass is somewhere on the order of 100,000 kilograms. So I'll put that number in. Okay, so now we have a force of gravity. Now you might notice that it's negative 9.81 times 10 to the 5th. Why so big? Well, remember, this is the force. The acceleration comes from F net divided by m. So if we take these two formulas that we already wrote down and take the quotes away and really write them, you'll see that it actually works out to exactly where we were. Acceleration equals F net divided by m, and both of those change, so I don't need absolute references. F net is equal to F gravity plus Fr. So here we are, back where we started. Let's drag this all the way down. Uh-oh, I broke something. Let's see, divided by H7. Oh, it's saying that there's no mass after the first one. That's okay. Let's just give it a mass for the time being so that it doesn't get too upset with me. Oh, and these formulas aren't copied down. Okay, but either way, you see that the actual first acceleration is negative 9.81, exactly where it was. Now, this is because we haven't really changed anything yet. It looks like we've made it more complicated, but we're still assuming that the only thing affecting this so far is the force of gravity. We know that's not the case, though. We know the rocket is also pushing very, very, very hard. How hard? That's a number that we have to look up, and I believe I got it for you. In fact, why don't we just go to Schoology right quick. Alright guys, sorry about the weird splice in the video, but I decided to make my computer cack out on me a second ago. So we're back now, and where we left off was we were saying, boy, wouldn't it be nice to have the information about this rocket that we could use. So fortunately for you guys, all this information that you'll need is already in the Schoology assignment. So one of the things that we wanted to know was the empty mass of the rocket, which is right here, 131,800 kilograms. No big deal. And then we also find out that its fuel mass is 601,200 kilograms. So we can make this equal 601,200 plus 131,800. That's the original mass of the rocket. And let's just drag that down a little bit for the time being. The thrust of the rocket is 9,420 kilonewtons. Remember, kilo means 10 to the 3, and this is already in the thousands. So the thrust from the rocket is 9.42 times 10 to the 6 newtons. There's our thrust. So now you'll notice that the net force is positive, not negative. Before I put this in, undo it, we had a big negative net force. Now we have a big, we have a big positive net force, except that I broke it, equals 9.42 times 10 to the 6th. Okay, so it looks like on first glance that we have all these things working. F net equals, add these two up. Fg is the formula for gravity. Force of the rocket is the thrust. And then mass is the fuel plus the mass of the rocket. So, here we go. Let's take all these formulas and drag them down. Boom. Uh-oh, we went too far. Let's just put it to here. All right. Now, something that you may not notice is that the numbers that we have here are not quite right. There's a couple reasons for it. Here we are, 265 seconds into our launch. And if you go all the way to this rightmost column, the mass of the rocket is still the same. That's kind of weird. Not only that, if you look at our column for C, which is telling us our velocity in meters per second, it's saying that we're going about 820 meters per second. Now, if you recall from the video that we watched earlier today, the astronauts said they were going about 7 times the speed of sound. This is only about twice the speed of sound. So something's up. And one of the things we have to be careful of is when you're working with spreadsheets like this and working with a whole bunch of numbers, it's very easy to just get complacent and say, well, I have a whole bunch of numbers down. They're probably right. But in this case, they're not. So let's think about this a little bit. First thing, force of gravity doesn't really look like it's changing much at all. Should it? Well, yeah, as we get further away, it should get smaller. Let's go all the way down and see, oh, it does start to change. It gets a little bit smaller, so that looks good. Net force. Well, the force of the rocket's not changing. Force of gravity gets a little bit less, so we would expect that would behave kind of the same way. Go down a little bit, or sorry, go up a little bit, it does. The actual acceleration stays pretty constant, so does net force. So let's look at these two last columns. The force of the rocket. Now, if you look on Schoology, it says that there is a thrust of 9,420 kilonewtons, but that it only has a burn time, the first stage burn time of 242 seconds, which means that this is the same the whole time, but only if the time is less than 242 seconds. So we could go and put in a little bit more of coding into here and do something creative to make it work. Because what we want to have happen is once we get to 242 seconds, somewhere down here, this should shut off. It shouldn't be pushing any further. So let's go up here, and we're going to put a simple thing called an if statement in here. So I'm going to take away this formula, and instead of just writing the number, I'm going to write if. And you'll notice that this little message pops up. I'm going to put parentheses in. And an if statement says, check some condition first. So I want to know what time it is. And if the time is less than 243 seconds, then, comma, I should get the velocity, the force 9.42 times 10 to the 6 newtons. Otherwise, comma, give me 0, no thrust at all. So here's your if statement. First thing is check a condition if the time is less than 243. Second, take this big number here and put it in if that condition's true. Third, take this little number here and put it in if the condition's not true. So I'm going to hit enter, and we're going to drag this formula down, and it doesn't really change anything just yet. But let's keep going down. All the way to the bottom. And you'll notice at the bottom it's zeros. Well, where did it change? Right here at 243 seconds. So you just programmed, or we just programmed the computer to make a decision to stop having the rocket thrust after a certain amount of time. Now, if you look over at the next column, mass, you might think something's kind of strange because the mass doesn't change with the rocket. But we know that a lot of the mass is tied up in fuel and only some of the mass is the rocket. So it doesn't really make sense for it to be this big number the whole time. Really what we want is for this number to get a little bit smaller as the fuel is being burned. So let's do a quick side calculation really fast. Alright, so we're going to go over here and we're going to say the thrust time is 242 seconds. And over that amount of time, we have 601,200 kilograms goes away. All that fuel goes away. So if we were to say, what is the mass divided by 242, we find out that 2,484 kilograms of fuel are burned every single second. But we're not doing anything about that. We got to take that into account down here. So, how can we do this in a clever way? Well, that's up for you to figure out. Based on that if statement I showed you, you can actually rewrite this mass statement a little bit. If you'd like me to help, I'd be happy to sit down and work with you on it. But it's your job to kind of figure out some way to take that into account. Now, I'll give you a little bit of a hint. This number is always going to be there, but this number is always going to change. So what might help you is to make this column the total mass and make this column the mass of the fuel. Because then what you can do is simplify this a little bit by saying, take the total mass plus the mass of the fuel. And here you can put 601,200 for now. But eventually what's going to happen is that number will go down. Now, remember, it's not going to go away just like the force from the rocket where it just shut off all of a sudden. But you can kind of get it to work in a similar manner. But like I said, I will leave that up to you. But that should do it for the most part for the A assignment. If you're going to do the M assignment, there's not really much more to it. The only big change you'll have to make is that we no longer want the information about Earth, we want it about your planet. So that should do it for right now. Enjoy, and I hope this helped.